we're looking at Chapter 5, Part 2 of our second law of thermodynamics. And now in this section here, we're going to be concentrating on the Kelvin temperature and the maximum performance. So this is a small section of our Chapter 5. So looking at the Kelvin temperature scale, here we have our heat engine, and we have two heat engines, and they're going between the same two temperature reservoirs. And so we have for each one of these, and these are reversible. So if heat's going in, QH, and then heat is leaving out, QC. And a lot of times it takes some work out of here. And one thing that we mentioned when we have our reversible process here, if they're going between the same two temperature reservoirs, their efficiencies, their thermal efficiencies, if I'm looking at a power cycle here, are equal, right? The thermal efficiency of our heat engine 2 is going to equal the thermal efficiency of 3. And recall, a thermal efficiency is 1 minus QC over QH, right? Then we have that ratio of our heats. And one thing that Lord Kelvin did is he took and he came up with this relationship. As long as we have a reversible cycle, the ratio of heat coming out and heat going in to our reversible cycle is the same as the ratio of the two temperatures of our high and low temperature reservoirs. Keep in mind that this must be in Kelvin temperatures. It has to be in Kelvin temperatures. And the other thing to keep in mind is that this only works if QC doesn't equal 0, and the temperature of the low temperature cannot equal 0 Kelvin. This would violate the Kelvin-Planck statement. Due to the Kelvin-Planck statement, we can't have QC equal 0, right? We have to have both temperature reservoirs. If QC was equal to 0, no heat leaving our reversible engine, that violates the Kelvin-Planck statement. Next, we're going to look at what we can do with our Kelvin-Planck statement, right, with the second law, and keeping that in mind as Carnot corollary with the statements is that if we have two systems, one reversible and one irreversible, going between two of the same hot and cold reservoirs, then the performance of the reversible heat engine is going to be actually greater than if there's irreversibilities present. And we've stated that before. And that also goes with our heat pump, right? Our heat pump or our refrigerator, okay? If going from the cold to the hot, putting work in, the reversible has a higher coefficient of performance than when there's irreversibilities present. Keeping this in mind, we can calculate the maximum theoretical thermal efficiency and coefficient of performance. If we look at a power cycle, we're looking at our thermal efficiency. We can use the temperatures instead of the heat. So if we use the temperatures, that will give us the max, the theoretical max of the efficiency we can get for that particular heat engine. If we look at refrigerators and heat pumps, again, if we use the temperatures in place of the heats, we can get our maximum coefficient of performance. One thing to keep in mind, all these temperatures must be in the Kelvin or Rankine scale. Cannot use Celsius or Fahrenheit. So it's something to keep in mind when we look at these particular scales. So let's do an example here. Let's do an example. In this particular example, we're looking at, we have two reservoirs with two different temperatures, and we have given the heat coming in and coming out. Okay? And so we have our system undergoes a power cycle. And right, we have a power cycle, and we want to determine if this power cycle is actually has any reversibilities, or if it's impossible. Okay, our scheme is already drawn for us. We're trying to find in these cases here, we want to find the actual efficiency, and we want to find the maximum efficiency, and then compare the two. And these are going to be at these three temperatures here, A, B, and C. So let's look at that. Let's look at our actual. Our actual efficiency is, go look, we have 1 minus, and the ratio of our heat coming out over our heat going in. And so when we look at this, this is 1 minus, and we have our QC, 600 over 1,000 kilojoules. So that's 0.6, subtracting from 1, and we get an efficiency of 0.4. Okay. So that's our actual. Now let's look at our each one of these cases, A, B, and C, our max. So we're looking at the max, and that's going to be 1 minus TL over TH, or TC, low over high. So our low temperature in the first case, let's look at A. We have 1 minus, and our temperature low is 200 Kelvin and 500 Kelvin. When we do this math, that comes out to be 0.6. So if we're comparing our Q max to our actual, right? And if we have 0.6 and relative to 0.4, the actual is actually less than our maximum. So we have irreversibilities present, right? There's some irreversibilities because it's less than there. If we look at B, and here we have 1 minus, we have 300 divided by 5, and that equals 0.4. If our actual is equal to our max, then our system is reversible. Okay? And if we look at C, and C we have 400 divided by 500, and we find that this is 0.2. And so if our max efficiency is only 20% and our actual is at 40%, right? So our actual is greater than our max, then this is an impossible situation. It doesn't happen. So one thing about the second law, it tells us if our process can actually occur, and this is one thing that we can use to look at that.